A very good morning everyone. Today my topic is about index modulation for high 5G, striving to do more with less. I am Jinaresh from ECE section. This is the PPT of ITC subject. I am studying in IRA college. Introduction. The explosive increase of mobile data services and the use of smartphones require the 5G network to support higher spectrum efficiency, that is SC, and higher energy efficiency, that is EE, and higher mobility. The current exponent modulation technique based on the multi-input multiple output orthogonal frequency division multiplexing MIMO unfortunately are not sufficient to satisfying such 5G requirements. Conventional multiple input multiple output may achieve high spectrum efficiency with massive antenna but has compromised energy efficiency due to the scaled power consumption of the large number of RF chains. The OFDM modulation is prone to Doppler induced inter-carrier interference. This inherent high peak to average power ratio also necessitates expensive power amplifiers. Novel advanced modulation techniques are therefore very much needed. To this end, the recently emerging index modulation techniques arise as a promising candidates with the potential to meet the 5G requirements. IM refers to the family of the modulation technique that relate to the activation states of some resources building blocks for the information embedding. We systematically establish a general framework unsatisfying space, time, and frequency in the which IM can be applied individually, computationally, and jointly. We then put existing forms of IM into the general framework in order to facilitate a systematic delineation of these pros and cons. For this, we aspire to shed light on whether index modulation can really do more with less. The index modulation family. Existing index modulation schemes are mainly carried out in the space, time, and frequency slots, or the combination of them, among which the most marked similarity lies in the utilization of active radio resources to carry information. Generally speaking, IM splits the information bit into index bits and the constellation bits. The former determine which portion of the radio resources, such as antennas, subcarriers, etc., is active, and the latter are mapped to conventional constellation symbols that are to be carried by active resources. Suppose that k out of the n resource indices are active. The system SC is term of bits per second per hertz is this SIM is equals to 1 by n log 2 CKN by index bits plus K by n log 2 of M constellation bits, where Cn of K denotes the binomial coefficient and M is the cardinality of the symbol constellation. Figure demonstrates the index mapping of existing IM schemes in different domains. This is the figure, and the evaluation of the SC and EE. In this section, we investigate the SC and EE issues in the index modulation systems. To evaluate the energy efficiency, we derive the coding gain of the index modulation schemes GC, which can be obtained by evaluating the high signal to noise approximation of the theoretical average bits error probability, where gamma denotes the signal to noise and GD is the coding gain. Know that this practice the system energy consumption should also account for computational complexity and circuit component power efficiency, since the transmitter side RF chains contributes the largest portion to the signal power consumption if the schemes have similar hardware costs and also similar computational complexity. The EE is solely determined by the coding gain, which determines the uncoded error performance and indicates the target RF transmits power to guarantee reliable transmissions. Enhancement of index modulation. Based on the fundamental concept of index modulation in space, time, and frequency, various paper aims at the improvement of the SC and CE and the potential of transmit diversity, pre-coding, and the other enhancement of the current IM techniques. Due to the similarity among different IM techniques, the enhancement proposal for the specific schemes are usually applicable to all the IM techniques. In this section, we introduce some recently proposed enhancements tailored for the IM in order to meet the demanding needs of 5G. To better illustrate this figure, we present these three typical enhancements designed for SM, which can be readily to this generalized to other IM schemes. These are the three sections. This figure shows the index mapping strategy in enhancement special modulation systems of a quadrature, spatial modulation, pre-coding aided spatial modulation, and space-time block coded spatial modulation. In phase quadrature index modulation, the RF signal usually contain in-phase components and the quadrature component. The orthogonality between them can be exploited to improve the SC of the IM techniques. For example, given a symbol drawn from the phase shift keying, quadrature amplitude modulation QAM constellation, one may map its real part with the cosine carrier into a randomly selected antenna and the imaginary part with the sine carrier to another randomly selected antenna. This technique termed as quadrature SM and retains the requirement of a single RF chain while allowing more spatial bits to the transmitter. The frequency domain counterpart of the OFDM with the in-phase quadrature IM is shown to have significantly better error performance than IM. OFDM has the same C. Pre-coded IM. IM is not limited for transmitter design with transmitter side CSC effective pre-coding techniques such as zero forcing and MMSC pre-coders and facilitate parallel interference free channels at the receiver antenna. Therefore, IM techniques can be transplanted to the receiver side by selecting the active receive antenna indices. Pre-coding aided SM PSM can be formulated as illustrated in the figure B. Different from SM or GSM, the detector of the constellation symbols at different antennas can be performed in the parallel manner, thereby significantly reducing the receiver complexity, especially when the multiple antennas are activated. Also, in order to bypass channel estimation in the PSM or DSM can also be applied at the receiver side, which also induces 3 dB performance penalty. Index modulation is in the space frequency domain can also applied at the receiver via precoding. With precoding, the received signal at different receive antenna are free of inter-channel interference. As a result, the joint selection of active elements in the space and frequency domain will not increase the detection complexity as at the transmitter side, which will allow more flexible grouping across the space and frequency domain to reduce the intra-group channel correlation and consequently improve the error performance. Diversity enhancement IM besides of SC improvements and receiver complexity reduction, research studies have been dedicated to the error performance enhancement of IM. Among these diversity enhancement IM schemes are attracting increased interest since the IM is natural applicable to multiple resources. Some well-known space-time block code such as Almonty can be integrated by carefully designing the mapping of index bits. Such designs are usually aggregated among different IM schemes be given similar channel properties, especially the coordinate interleaving method proposed for IMOFDM is also applicable for all the pre-coded IM scheme because this pre-coding the received signal among the receive antenna becomes interference free. Applications of IM. The implementation of IM is various communication scenarios is also a hot topic. The 5G communication system is expected to accommodate several emerging communication technologies such as massive multiple input multiple output cooperative networks and the full duplex radio, as well as the supporting the quality of the service requirements in challenging environments such as high mobility scenarios. In order to better meet such needs, basic IM techniques should be further tailored and extensive theoretical studies are needed. IM in massive MIMO has been recognized as one of the key techniques in 5G. With hundreds of antennas at the base station, the SC can be significantly boosted and the multi-user interference eliminated. Pre-coding is a natural way of integrating IM techniques into a multi-user massive IMMO downlink. Data transformation of multi-user can be accommodated in the same frequency band via space division multiple axes, and the detection complexity can streams transmitted to the receive antenna as well isolated by linear recording at the base station. IM in full duplex communication. Full duplex is promising technique for the achieving high SC in wireless systems by transmitting and receiving radio signals simultaneously at the same frequency as the communication node. IM or the cooperative communication. Cooperative communication is widely considered to have promising potential to of lower cost, improved AC and extended coverage. Naturally, combination of IM with cooperative communication is also drawn increasing attention. IM in high mobility scenario. The rapid progress of the high speed railway systems bring out an urgent need for the high speed data-less wireless communication in the high mobility scenarios. Due to the significant Doppler, the accurate estimation of CSI will mark improving the system complexity. SM in reported to have 3 dB performance also from SM with channel estimated errors and preamble overhead. In the high mobility scenario, SM may demonstrate improved performance. However, the design of differential IM schemes in other domains still remains to be investigated. Conclusion: we have introduced the concept of IM to improve the SC and CE for the next generation communication systems. We have shown that the proper design IM can be flexibility applied in space, frequency, and time domains. We have discussed various enhancement and situations IM schemes. Furthermore, applicability for the error performance. We have also revealed the promising potentials of IM in the massive IMMO high mobility scenarios and cooperative communication systems. Last but not least, we have delineated the opportunities and challenges of IM design for 5G. Thank you.